Hello internet friends. I am diving back into the Go Ethereum Geth codebase and gonna have a look today at consensus and this whole folder just on the Ethereum consensus mechanisms. So I've already had a bit of a quick look at it, but haven't dived too deep into it yet. So ETH hash here is, I guess, the main proof of work mechanism that Ethereum uses, and then it's got a couple others floating around just for like test nets and stuff. So if I go to the code base and go into the consensus folder and we start digging into it, we are going to find a lot that's named about this ETH hash. And I think I'll start here in this ethhash.go folder file. Mostly because when I had a look at it before, there was a structure called ETH hash, and it looks like where meat of the code base is. So let's see if we can find some structs. So config file for it, and here is ETH hash. And this file almost like it's quite small. It kind of looks like it's mostly just like this ETH hash structure, and then a new function to create a new one, and just everything after this point is pretty much like there's some test stuff, but it really just is like establishing this ETH hash structure. And then when we have a look at some of the other files in here, say consensus, I think they're all just extending this ETH hash structure. And if I go down a bit, you can see that these functions here, like verify header, are just building off of this ETH hash. So if I see here, we've got the fake stuff here, but right here, this new function, this is probably going to be the entry point. So let's see how we can find where this gets built, where it gets called, and then I guess what the blockchain is doing with it. I mean, I've got a pretty good idea. Like, it's gonna start with the blockchain, and it's probably gonna call this verify header. So that might be a good way to start. Actually, is back verify header. Let's see what comes up. And here we are already straight back into where we're looking. So these two are probably just digging into the files anyway. There's click, which is the proof of authority, I think. Test, header chain might be close. Blockchain looks very good to dive into here. And I already know that this engine structure on the blockchain structure is the ETH hash structure we're looking up back here. So they start with the blockchain. It has a reference to this ETH hash structure, and then they call it to dive into when they need to check what's going on with the blocks and stuff. So if I go into core blockchain and look at that BC engine verify header, we'll probably see where we want to go. Up a bit, into core, into blockchain, and then it was 344. We can get out of this now. So here's a good place. And when we scroll up a bit and find what function we're in, it might give us new blockchain. Interesting. Okay, so this isn't actually where it's doing any work at the moment, but it's just like initializing stuff. So I'm assuming this new blockchain gets called by our node when we start up. So if I go back into here and act new blockchain and see where it gives us. So there's some more tests, there's more tests, everything under up to this point in this search has come back as tests. More tests, state processor tests. Almost all of them are going to be test. And then there's going to be one where it's called once. And it's actually in, there's our function definition there. And when we go more Genesis test, simulator test, worker test, minor test, handler test, backend.go looks like a winner. So if we go up here and go find our Ethereum backend, we can see where we call and we can just start from the start. We've got, where is it? Backend. Cool. So in backend, we go to 191. And in here, where are we? What function are we in? New. So this creates a new Ethereum object and it lives on the node, I assume. Considering we're passing a node back. No, we're passing Ethereum back, but we take a node. Take a node in the config. And then in here, down a bit, we call this Ethereum blockchain and we pass it a bunch of these configs. This eth.engine is going to be our eth hash. So if I try find where this engine came through, Ethereum config create consensus engine, and it's passing a bunch of like stack configs, minor configs. It's just a bunch of configs. So let's find this create consensus engine. And is defined in eth config, and on 207. So in here is where they create the eth hash consensus engine, and then it returns it, which then gets passed to our, when we create the blockchain, we pass this engine in, and then it simply saves it in the blockchain structure in this. So we pass it into this new blockchain function under blockchain.go. And then down here, it actually does some verify headers for current headers. But I think this new blockchain, I'm not sure if it actually is loading in blocks at this point in time, or if it's just, there's a Genesis block, get block by number 0. But yeah, so we're just creating a blockchain. We know we've got this engine on it, and that's where we can verify headers and probably a few others. So in here, get config, what are we doing? It's calling ethhash.new, which if we go back into our ethash here, it's going to new, and we're booting up, and it's passing a config here and returning just the structure that we've defined above, and it's doing not much with it. It's just putting in the config into its namespace, I guess is what you call it. Checks if it's proof of work, and if it is proof of work, it allows it to exist, I guess. But I guess at this point, I feel like it already knows it's going to be proof of work, because it's calling eth hash. but it is passing proof of work config to it. But here we've got click. So it's if the config says click, we do a new one and then return that without even coming here. But that's just proof of authority, so I guess that's testing and whatever. Don't really want to dive into that because it's less interesting. So we create a new ETH hash, pass in proof of work, and a bunch of uninteresting config items, I guess, about the database. And then that gets passed to our backend when we create our Ethereum object. Engine, where'd that go? And the Ethereum object then passes that to the Ethereum blockchain object. And all that does is it saves it as engine under the blockchain. And that's, I think, where it's going to be referenced, is you have access to the blockchain almost everywhere, that blockchain structure, and it'll just say call blockchain.engine. whatever you need the engine to do. And the very first one that popped up, and probably the meat of it all, is this verify header. So what's going on there? In this blockchain, we have just created. So when the server just starts up, creates it, saves this engine onto it, and then it goes down and only gets called here verify header, and you pass it the blockchain and a current header. What is the current header though? Have they done anything with it, I guess? State.new. See, this is all initializing, like they've got that state structure. And it's just creating it so they can, down the future, do stuff. So the blockchain.genesis block equals blockchain.getBlock number 0. They create this new header chain. And this header chain, I'm not fully sure what this header chain means here, but I'm assuming it's just block headers, which is not got transactions in them, so it's just like the top of it and a link to the transactions. But again, I don't think at this point there's any actual blocks on it. So down here where it's calling verify header, and here we've got a comment. First thing the node will do is reconstruct the verification data for the head block. Reconstruct the verification data for the head block. Not sure what that means. I guess it just needs some config stuff, and if you pass it in with the, I guess, the Genesis block, it does nothing but it'll learn from it. So for hash, make sure we don't have any bad blocks in our chain. It's kind of reads like it does have some blocks in it though when I'm reading this code. Return blockchain. Cool. So maybe that's not where we want to be. So if we look a bit more, we want that verify header. Where else is it called? Those consensus ones, I'm assuming the definitions. Click is definitions. Blockchain test header chain.go. ETH.handler. That's interesting. So in this area, let's get out of that one. We want to be in ETH. Regular sounds like a good place to be, because it sounds like it'd be like handle the blocks as you get them over the network. So verify header, collect the fetcher, and you can see here it's the same deal. We've got something with the chain, and then we've got an engine. We've got this is a function to get it out, but then we're calling the verify header on it again. So that engine is our ETH hash, and it's getting called everywhere. A new handler. So this handler is another structure. It's, I guess, getting passed around, and it possibly is what gets handed the blocks when things get received. So the network comes in, it receives a block, potentially has been given straight to this handler, and in it, it's got this validator. Construct the fetcher. What's a validator? Block fetcher. No, it's a local variable. So it's a local variable passed into this new block fetcher. That sounds like when we're starting up, the block fetcher is the one that goes and gets a bunch of blocks. And then it's got this chain sinker. So maybe this header function, verify header, is not exactly where we want to be. What else have we got in here? Verify headers. And then we've got verify header worker. I mean, this kind of sounds like it's able to pass off this ability to check headers to more than one thread. So when you've got a bunch of blocks coming in, you can pass it a worker, and all it's doing here is calling verify header. We've got verify uncles. Doesn't sound super interesting. If you receive an uncle through the network, I guess you probably want to check that too, which is just you need to do. More verify headers. These are all internal ones, so that big verify header, I guess, is the main one. Calculate difficulty is interesting. This is going to be where the blockchain checks what the difficulty should be depending on when the blocks have been mined. And it's also got built in all this stuff is like the time bomb. So they've created a thing that says, do you have the time bomb going off before? I guess it is London. And it just returns calculate difficulty for EIP 53554. I wonder if that's defined in here. Make a difficulty calculator. It's probably being called by those ones. And we've got some 3551, 3554. Yeah, okay. So they define this calculate difficulty as make difficulty calculator. And they pass it this. Is this a block? What's the Ethereum blocks at the moment? We are at block 128. 12 million. So what's that? What did they put in here? Nah, it's a different block. Interesting. Must not be a block. Let's see this. When does that come in? Fork block number. Oh, it's passing 9.7 million blocks later than the actual block number. And we're at block what? 12 million. So we fork and then 9.7 million blocks later, it'll start having that difficulty increase. Yeah, okay, cool. I mean, how it calculates that is probably just some like exponential, and it just goes up slightly every block and then increases the higher and later it goes on. So all these ones call this function bomb delay. And creating some ints, subtract big time minus big time parent, compare if that is less than 0, then it's a minus, then if it is a minus, I guess it's going to be to be honest, it seems less interesting, but I guess like the rest of this whole function isn't very, file isn't very big, so it's probably like all these calculate difficulties for all the different types of forks that they've had, with London being the latest and what's going through it. Prepare implements consensus engine. Finalize implements consensus.engine. Accumulating the block and uncle rewards, setting the final state on the header. Interesting. Header.root is intermediate.root. Finalize and assemble. I guess consensus.engine is a interface, I guess. Is that this? Chain header reader is an interface that needs all these. Chain reader needs those, and engine. So yeah, so they've got this. If we look in here in this consensus, they've defined this consensus interface, and then they're just saying that eth hash and click and who even knows what's in MISC forks. This is a list of forkers. That's uninteresting. Deo hack. Is this? Yeah. File specifically for the Deo hack. Anyway, so that I guess is exceptions. So consensus here defines what consensus here and also here probably has something similar in it needs to be. So eth hash needs to implement all these functions. It's on consensus here, which is author, verify headers, verify uncles, prepare, finalize. This is probably actually an interesting way. This is where they've defined it all. So there are consensus fields on a block header according to a particular engine. Fun. So I guess this is getting called when a block is being created and then that gets passed what the results of this is. This header is probably initializes the consensus fields of a block header. So it's probably passing in that header and then making changes to it. Finalize runs any post-transaction state modifications, block rewards, but does not assemble the block. block header and state database might be updated to reflect any consensus rules that happen at finalization. This is, they've said block rewards twice here. So I guess it's just adding the Coinbase to the header. Finalize and assemble runs any post-transaction state modifications and assembles the final block. Cool. Seal hash, calculate difficulty we saw before. Proof of work interface has an engine and a hash rate. So when you're running a miner, I guess it needs to know that it needs to have access to that. Yeah, okay. So when you're running a miner, you'll have to have this proof of work, so you can call the engine and, you know, seal the block, I guess, and prepare the block, and then you'll want to know what your hash rate and stuff is, but only if you're running a block. So I assume that this consensus engine is used in two places, being the like when the miner creates a block, and also when a block is received over the network. So this engine is really just verifying headers. So maybe it is in this handler. Let's go a bit deeper in this handler. Actually, now let's see what else we've got. So we know what this interface is. That's not so fun. We've got an algorithm. What's in the algorithm? This is a bigger file. See if we might come back to that later. API exposes related functions. Get work. Yeah, okay. So this is all, if you were to have the RPC client going and you make calls, it gives you like the hash rate and stuff. So you can actually call what your hash rate is from an RPC call. Less interesting. Difficulty.go. Is this where we were before? Make difficulty calculator. This is all very probably interesting math that needs to be dived into at some later date, but just looking at it now is not too much. But I assume it's just basic, like you define a number and that, you know, some number to that is an exponential, like 2 to the power of whatever it is. There's the time bomb there. Like you just take the difficulty, raise 2 to the power of that difficulty, and that gives you your hash that you have to be lower than. Something like that. Conceptually, I don't think it needs to be more than just like, hey, there's a number you need to make your hash lower than. I mean, math could probably be interesting, but that's probably not all there is in this Ethereum ETH hash. And sealer. See, I don't really understand what sealer's doing. I guess it's like finalizing a block when you create it. Seal implements consensus. Okay, so they just keep saying implements consensus.engine. Attempts to find a nonce that satisfies the block's difficulty requirements. So you can only call. So you make your block when you're mining. You put in yourself as the Coinbase, and then you also put in all the transactions you want to. And then after you've done all that, you call seal, and it will start a bunch of threads, giving them like a random number, and yep, initializing some threads, pushing a new work right to a remote sealer. Create a seal task with the block and the results. And you go through each of the blocks. Pend.add. What's pend? You've got a wait group. Okay. So just defer pends.done eth_hash.mine. Interesting. Where is this mine defined then? Maybe an algorithm? Nope. Mine. Oh, by the looks of it. Difficulty consensus sealer. Do we have a miner or something in here? Like, yeah, we do. It's under Ethash. This isn't a different namespace, so it can't really be it. So we've got Ethash. What's Ethash in this? Is it actually the... We do have Ethash, yeah. So the Ethash structure has a mine function on it. Is it a function or a mine block ID? It does. So somewhere in it you can call mine on it. And I guess it goes and digs up the miner. Kill some of these extra files. Actually, let's go into this consensus and see if we can find it. Mine. There's lots of mines here. They're all in comments, so. Ethash test, sealer test, mine result. Mine, here we go. There, it's defined right there. So the function is, it's in sealer. It's where we were. Q exit. Slash mine. Here we go. I might have missed that before. So mine is the actual proof of work miner that searches for a nonce starting from a seed. So you pass in a block, you pass in a seed, which is that random number, so they don't clash if you're running multiple threads, I guess. You got eth.sealHash header bytes. So seal hash, where's hash? Get cold. Hash rate. Hashimoto full. Create the proof of work value of this nonce. Hashimoto full with the hash. Let's see what. I think this is something that's probably like got some interesting like research behind it. Hence why it's named. And I have heard of Hashimoto somewhere. So mining algorithm, it has been succeeded by Ethash. Interesting. Does it call it still then, or is this like surrounded by a if version or something? Ethash. If cases abort, gets out of it. Copies a header, copies a nonce. Returns the block if still needed. Interesting. So this colon is Hashimoto full, which isn't like, I thought Hashimoto was killed, I guess. So for them to say that Ethash is still using Hashimoto full. What does it say here? It's built on two key pieces of work. Hashimoto algorithm and dagger. Hashimoto dagger might be what's phased out. Whereas Hashimoto is like just the name of the hash, I guess. Has been replaced by Ethash. Have I got a link? here. Moving, ETH hash. Oh, cool. Linked. Is a planned proof is the latest version of Dagger Hashimoto, although it can no longer appropriately be called that since many of the original features have been drastically changed. There exists a seed which can be computed for each block by scanning through the block headers up until that point. From that seed, we compute a cache. From this cache, we can generate a 1 gigabyte data set with the property that each item depends on only a small number of items from the cache. Full miners and clients store the data set. The data set grows linear with time. You grab random slices of this 1 gigabyte data set and hash them together. Okay, cool. So they've just defined how like the hashes have to be like the procedure for hashing to generate this like hash. And what it does is you have to generate a gigabyte worth of data, and then it probably has like random. So I guess that seed here that gets passed into this is actually not a random. Maybe that ID is. I thought I saw it before. Slash mine. You blast a block, the ID, the nonce, and abort. So ID is less than this ID is iterated for every thread. So the second one, block ID, the nonce is passed in this ETH hash random int 32 number. So I'm reading that as it's generating a random number here and passing it into this ETH hash.mine block. And then once you get there, it'll either true or false it and say, hey, look, that block that we've passed, it does take that seed. Start an ETH hash search for new nonces using a seed. Interesting. So for every thread it generates a random seed, passes that in here. And that seed is used to generate no idea. Where is this channel being called? Little board and channel. For select case abort. So this is just saying that you can abort it later on. So while it's not aborted through that channel that's passed in, we don't have to update the hash rate on every nonce. So you make a hash. Where is hash created from? CL hash header. Target number data set. Difficulty header.difficulty. So you get your target, which is your header.difficulty. And that's defined in this like consensus, like depending on the difficulty bomb and blocks and how fast they're going, tells us what the difficulty is, and then that comes as target. So at some point this target has to be called. If you compare the result with target is less than 0. So where's result? Back. Okay, results here. So Hashimoto full takes in this hash, it takes in the nonce, and your data set, which is your 1 gigabyte, it gives you a result. And you compare that result to what the difficulty is, and if it's less than the difficulty, then it's a winner. So correct nonce found, create a new header with it. So you take whatever the header is and you make it, and then you return the block. And if it's not, you increment the nonce. So where's nonce defined? Nonce equals seed. Okay. So seed is a random number. And then you use that seed and that nonce. Seed goes there, nonce seed. Where's nonce seed defined? Nonce minus seed. Derp. Cool. So miner goes in. You mine the result. It takes a seed for random. Where's my miner? Gone. Yeah, so it doesn't go over each thread, pass it a random integer into its nonce. It's calling this function id nonce with I and nonce. So you pass in nonce in for every thread you're running the miner on. And then it's taking that nonce, iterating over it, incrementing it here by 1 if new rep. And this is the loop here. So it's just an infinite loop, and it exits when this abort is called. And we go through it, we call this Hashimoto full, we pass it our nonce, and we get this result. And then we compare our result with our target, which is the difficulty, and if it's less than that, we win. That's great. So do we have Hashimoto full here? That's going to be in our miner. It's in ETH hash algorithm. Oh, right, okay, cool. So this is this big file that I've not dived into yet. So Hashimoto. Lookup. Pass it to Hashimoto. This function aggregates data from the full data set in order to produce our final value for a particular hash and nonce. How big is this function? What was the bet? It is. I was going to say huge, but it's not. We got Hashimoto light, Hashimoto full. This algorithm is all about this Hashimoto, not Hashimoto dagger. There's a bunch of random values that is going to be used in the hash. So it kind of sounds like it takes a random number, generates from that number somehow 1 gigabyte worth of like random data, pseudo random, and then it picks random sort of sections of that and does hashes over them. And you know, if they're all G, then we know that you know, the hash, you hash all those sections, then you hash those together as like a graph or something, maybe, who knows. And these are just static data for like, okay, so this actually isn't that bad of a file. All it's doing is defining lots. So it's got a cache, calculates cache size, it's got a data set, and that's the 1 GB data set. And you make a hasher, and you seed the hash. And this is all very like sort of not interesting stuff, and it'd probably be better coming into this ETH hash. Mining involves grab random slices and hashing them together. Verification of done with low memory by using a cache. The data set is updated everything. So what do those big things do then? Data sizes. The following lookup tables provide a function approximately 248 tabulated epochs. Oh, right, interesting. So they've just pre-generated data sizes and cache sizes. 248 epochs. Don't know what an epoch is in relation to a Ethereum 1. Anyway, this is sort of diving too deep into the mining stuff, which is kind of interesting. So all we know is we've got a block. The miner who is going to do it eventually creates the block, puts their stuff into it, grabs all the random transactions they want to put in there, then calls this sealer file, which has a seal function here. And then in that seal function, it starts calling the miner, the algorithm for the miner. AGSM seal. This might be too general. My search might be too big. Engine.seal. Miner worker. I reckon it's called in there. In this miner section. Seal. Make sealer. Click. Yeah, here it is. Seal hash. Engine.seal. Worker.go. So this starts delving into when they run the miner, which is its own maybe executable, but probably built into Geth. You've got where are we going? We're going up here, we're going into miner again. Trying to get out of miner, but we're stuck here at the moment. And in worker, /seal. Seal hook, seal hash. Where is this being called from? Task loop. Standalone go routine to fetch the sealing task from the generator and push them to the consensus engine. So we start with task loop. Where does this get called from? Worker task loop. We've got a new worker. Miner. New worker. So the miner has a worker, the worker calls the sealer. Sealer runs loops over stuff, which is not as specific as I'd like it to be, but it is kind of for. So it's got another infinite loop here. Seal worker chain task.block. So you pass it a block, and it calls it. This is interesting because that seal I thought did the infinite loop as well. Case new task. So this is only called if a task is added to the channel. So you add a task and it'll go through that task. And that task has a block that needs to be sealed. So this task channel on the miner, nope, it's not on there, task H. So to work as a task channel, commit not in here either. Commit, give me something. Recommit. So the worker, you call commit on the worker to add a block to the task. The task then gets pushed through to this sealer.go, which takes the block, spins up as many threads as it can, and it also just handles everything in this algorithm, which is less interesting, but it's mostly like predefined, I guess, locations. Is that what it's trying to say? Data sizes and cache sizes. I thought data size was 1 gigabyte. You got a 1 gigabyte data set. Each item in the data set depends on only a small item. Full clients of mine store the whole data set. The data set grows linear with time. So your seed defines what areas of that 1 gigabyte get hashed. Yeah, okay, that's kind of interesting. All right, so we're still in the miner territory here. So we know we got a miner, and in that miner we stress test for ETH. No. What is in this miner? How big is it? You're not very big. Not much going on. You create a new miner and you do not very much with it. Start. Now these are all just like handling the structure, like turning it on and off and giving it access to things, and it's all done in this worker. So anyway, you mine it until you get into this sealer. But what else does ETH hash do? You got a hash rate, which is also to do with the miner as well. I guess it all is in this verify header, isn't it? Is it in this way? Verify header. Nope. Consensus. Yeah, here you are. So it is this verify header that's doing it. So I guess handler calls verify header. click is not what we want. Test, nope, header chain. Header chain, possibly, is it? Where's handler? Light chain test, fetch it to go. Let's go back into this header chain in core. Actually, we hadn't gone into that, did we? So core header chain. GEHO chain. And it was on 341. And this function is called when validate header chain. So these all read to me like, so this is an array of headers. Might be worth figuring out exactly what is in a header. Header chain implements basic blocks. Types.header. Types on the core, do you reckon? Here we are. Header. What? You do have here. You lie to me. It's confusing me. Why would you have types? There's not there. There's under this one. Because there's lots of them. Hashing. It's a block header, isn't it? It's going to be under block. So we have our block header here. In your block, you have your parent hash, so it points to the earlier block. It has a difficulty which is defined by the consensus algorithm. Block number, I guess, is height. Gas limit, gas used. Gas limit, I think, might be this new London thing. Gas used is a total gas used in all the transactions, maybe. You got an extra in the block for when you mine and you want to put stuff in there, I guess. And you got your nonce, which is what you're mining for. And it's got a transactions root. So it gives you a bunch of transactions not listed in like an array of hashes, but it's actually like a hash that defines all, like a graph of all the hashes. And I wonder if header marshalling, what else is in here? You have a hash over the header. So they've defined this RLP hash, which is just like a standard way of running over a structure. RLP, I think, is just like, you make it alphabetical, everything in their header is alphabetical. That way when you hash it, you know it's going to be the same no matter what, who's doing it. It's like there's no vagueness in what their headers' names are and where they're located in the structure, like the data. Empty body, your block has a header. Here you go. So your block has your header, which has all your like roots, transaction hashes and stuff. Has a list of transactions here, and also has uncles, which is an array of more headers, which is pointing at other blocks that weren't there. So in there, you go through, you verify the header. So to verify the header, you validate header chain. So you pass in a bunch, like an array of these headers, which is your chain. And it loops over everything in them, and it goes through the chain number, and if it doesn't equal +1, this looks like your chain. Yeah, if the current one you're looking at. So you got your array at point I, the number, so the height does not equal the previous entry in chains, number plus 1. If it does, you do stuff. If you don't, then you've got a block that's going 1, 2, 4 or something. If the header is a banned one straight out of board, this has got a bunch of bad hashes. So it doesn't do any work if they're not in order. If it's the last header in the chunk, probably chunk is what they meant there. You check the seals. Make a list, an empty listed length of the chain. You go through each of the items, whatever check frequency is. Results equals verify headers, and you pass the whole chain to it. Then you iterate over the headers to make sure that they all check out. If the chain is terminating, stop processing blocks. So it's all kind of going like, hey, look, we've been given this big list of like a chain, which when I'm reading this, I'm kind of saying like, oh, most of the time this is going to be when you're starting up trying to sync, you're passing in like 20 blocks at a time or something. So if I go into ACK, validate header chain, this gets called in blockchain or header chain. So they must maintain like a header chain separate to blockchain. Core blockchain. Do I already have that open? No. So validate header chain, insert header chain. So it's really just passing on. Oh, let's do it again. Insert header chain calls the insert header chain. This has nothing in blockchain. Okay. Insert header chain. Where do you call this? That looks like a test. Test. Header chain chest blockchain test. Downloader. Yeah, okay. So downloader calls it because we downloaded a blockchain, which is less interesting because we want to get away from this like downloading a blockchain. And you more want to do when it's like, hey, we've received a block over the network, which is where it's potentially like I think it's like maybe you have your RPC and you receive a block from it. Endpoints, maybe. Handler. Block. Never handles blocks indefinitely because RPCs are processed in the background. Subblock. Subblock. No, this isn't gonna be anywhere. Where's this handler? That handler was interesting. Is that a core? ETH handler? Yeah, cool. Let's get out of you. Clear some of these files that I got open. New handler. So where does new handler live? Backend. ETH backend has a handler. Ooh. RPC server does too. So RPC server, I suspect, is where, like, if you have a node and someone is trying to connect to you, they connect you over the RPC, and it is where it'll be passed. Serve single request, and you pass in a new handler. If batch handle messages, handler handle messages, slash handle messages. Wait, what? It's not in here. Handle message. God, where are you? What am I doing? Why is this not working? HANDLE MSG. Why didn't that work earlier? So it is in handler. HANDLE. Did I do EL? It's RPC handler, not consensus handler. That's what it is. So where's that in this handler? Handle message. So you've got a single message for something. Handle subscriptions. Handle call message. Handle call message is like if you were running a smart contract somewhere and you call an RPC node and you call it. I don't think this is what I want. It executes the call message and then returns the answer. Maybe. What's in our like peer-to-peer like then? I suspect it's huge. Maybe too much to go into. But if we search for peer-to-peer handle, peer.go handles a message. Maybe that's where we want to be. Handles packets. Yeah, this is deep. There's a lot going on here. See if this handle has anything. Read loop. You got peer.handle. It's a ping message, discard message, has protocol left. It's a sub-protocol message. So the peer-to-peer layer has a bunch of things like ping and discovery, I guess. This is the case that does that. So peer.get protocol of the message. So what's get proto? Code. For proto in range.p.running. Finds the protocol for responsibly for handing the given message code. I think we're too low level. Proto read write. So somewhere in here message not handled. Still way too low level here. Let's go back to handler and see. We've got a new handler. Where does new handler live? New handler. On the back end. This is, you got a new backend, you got a new handler. You got a handler downloader. What else have we got? So these are all RPCs, have got their own handler in it, so I don't think they're related. ETH handler test, handler ETH test, handler. It's got to be in this backend. This is the only place that's got it. Accept transactions. Start mining. Back into mining. Handler downloader. Accept transactions equals yes. I still haven't found handle block. Handler block fetcher. This will sink in. Broadcast block. ETH test. Handler. Handler is not safe for concurrent use. Request test. LES. LES is like a light server. I don't think it's going to be in any of those. But it's this handler that's doing something. Current header, blockchain, subscribe. So verify headers is on this handler. Still kind of stuck in this, like, where does it call I have received a new block? Maybe it's not this. Where am I looking? We've got a blockchain. Git header. No. Let's go back into ETH hash. What do we got? What other cool functions are in here that we can like play with? It's always verify headers though. I guess so much about it is syncing. Calculate difficulty. Maybe that would be where we do it. calculate difficulty. What do we got? What do you got for me? Somewhere where you check the difficulty. Chain makers. Interesting. So we've got 3 test guys here, and then we've got difficulty.go. Consensus and consensus. Click another test, and then chain makers. What's chain makers? No, I don't want to buffer. Core chain makers. Calc. Offset time. Damn it. That's a dead end too. Set difficulty, offset time. Is ETH hash has the difficulty? Not in this one. London. Not in there, apparently. London. Calc difficulty is London. So there isn't actually that much to all of this. Algorithm is all about this ETH hash, the Hashimoto dagger stuff. Consensus is just validate header really. ETH hash is just a structure. Seal is like, hey, we call the mining function over a block once we've got it. So there isn't actually too much here about that. They still haven't found out what happens to give you a block. Who has a block? Block. Now the service is just going to be like starting up the RPC server and what do we do? Okay, let's look at this a different way. When we've got sealer, we have we successfully get a block. What happens then? Group, create our things, ethash.mine. If one of the threads found a block, abort all others. Great. Close.abort. thread count was changed. So they add it to this results. This results channel. Slash results. So seal gets called by the worker has a result. So in mining, it was in worker again. We got worker, miner, seal. No, it's not miner, it's worker. You have this results channel. The worker result channel. We've got the result loop. Chain.hasBlock. So we've got a block, we've received a block in our result loop. And then it does a bunch of tests to make sure there's not like duplicates or something stupid's happened. You get the seal hash out of the block. You get all the receipts out for some reason. Yeah, because you're going to announce it. Chain write block with state, you reckon? That looks interesting. Broadcast, new mind block event. So there's two interesting functions there. New mind block event. Is that ETH handler again? New mind. No, I'm in RPC. Which one? Consensus ETH hash. Kill some of these. Go into handler, see where we can find what it goes on there. ETH handler again, hello. Such new mind block. So when we start our handler, we subscribe to event multi to new block mind block events. Mind block sub. So when we get something to this mind block subscription channel, broadcast block. It gets its peers without block. Block without hash. Propagates it. Propagate is sending it to if handler chain.hasBlock. Async send new block hash. Block hash. ETH protocols ETH peer. ETH peer. Send new block hash. What I'm assuming async just wraps this in. For peer, known blocks cardinality. New block hash is payment. Yeah, async just send new block hashes. Send new block. Peer-to-peer new block message. What is that? Damn it. What have I done? Interesting. So ETH handlers new block message. Handle new block. ETH protocol 007. Cool. So you send a message to the peer-to-peer network and your message has 07 as its code, and then if it is that, then you would know that you received a block. But I think I'll drop it there because this is kind of getting into the peer-to-peer, and I think I've already been looking at this for an hour and a half now, so probably quite a long one already, and I might dig into some more in a second video. Cool. Thanks everyone.